before I go on, I know I absolutely whipped through chapter 5 because I didn't really do it. I just said you guys are all supposed to know how to do double and triple integrals. Recognizing that for a lot of people, those computations are going to be things you haven't done in a long time. So tomorrow, for the lab day, I'm just going to bring in a giant pile of integrals to do. If you don't want practice on doing the computations and integrals, you can go do something else. But I promise, most of the rest of the course is going to require that you can calculate double and triple integrals. So if you feel shaky on that, and you want to have some practice doing it, I will provide you a rich library of examples to work through. Okay. So what I want to talk about now is related to the idea of double and triple integrals, because we're going to talk about sort of 6.1, which I think brings together, so the chapter 6 is the change of variables theorem, which means that we're studying double and triple integrals in the correct way. Right. So in 241, we sort of barely got a piece of this. And I'm going to motivate this. So 6.1 precisely is called mappings from R2 to R2. It's sort of a technical chapter talking about maps of domains and two variables to other domains and two variables. We're actually going to start not with 6.1, but a motivation for the change of variables theorem. And the way that we're going to do that is we're going to revisit U substitution, which is a sort of technique that we all learn, but hardly anybody actually understands what's happening when you do it, right? It's an algorithm that you use for undoing the chain rule. Sorry. Okay, so let's consider the problem. The integral from, let's follow my notes here, from 1 to 4 of 2x e to the x squared dx. It's like baby's first U substitution.
That is not a 2.
What? That? Sure. Okay. So you look at that integral, and one of the things you do in U substitution is you say, step back for a second, like I'm going to find the most complicated thing I see inside of another function, and that's what I'll call U, right? The reason that you do that is because it kind of sucks there's an x squared up here. That's not in my table of elementary antiderivatives. And so I would like to write a function that does have that there. So it'd be really awesome if I could just let that be U, because I know how to integrate e to the U. Right? So then the method that you learn is you say, oh, wouldn't it be great if U is equal to x squared? Okay. Now, some of you learn this and some of you don't. This does induce a change of variables on the x that remains. So x is equal to the square root of U. That doesn't seem like you've really changed anything in a useful way by doing that. But let's just think about what this change of variables does to the function for a second. So the first thing that the change of variables does is it changes the domain that you're considering. So you started on the domain from 1 to 4, but if you feed this change of variables an interval from 1 to 4, what comes out the other side is the interval from U of 1 to U of 4, which is the domain 1 to 16. So you've sort of taken your original domain and changed it. Right? You ate the original domain, you produced a new one. The reason that I can just stab U in here is because this function is monotone on the interval that I stuck it on. Okay? Of course, the other problem is when you're doing an integral theory is that I know in the back, a lot of you are thinking, why don't you just do the 2u is equal to 2x dx thing? No, I'll get there. This is the next thing that's going to happen. I've left this for the last bit. So the other thing that I did when I changed variables is I didn't just change the interval from 1 to 4 into the interval from 1 to 16. I've not done that in a linear way. I didn't just pick it up and slide it over or multiply it by 4. I've stretched it in a way that's kind of weird, right? It's weighted more towards the 4. Things get big fast at the end. So if you want to see exactly what I mean by that, I'm making the claim that the amount that dx counts for, I should say, what I'm saying here is du weights small intervals differently than dx. I need something that's going to account for the fact that when I change the domain from this to this, I didn't just transform the domain itself, but the structure of the domain, which is to say that if I start calculating the effect of du and dx on little tiny intervals, if I write down something like, oh, how about I take a little tiny interval in the domain, like 1 to 1.1? What does dx do to that thing? So if you think about dx as a function that measures intervals, dx of that little interval says, oh, 1.1 minus 1, which is 0.1. That's what dx does, right? It measures intervals. Well, what does du do? du of that same thing is not going to measure 1 to 1.1. It's going to measure the difference from u of 1 to u of 1.1. u takes that interval and stretches it. du, as a measure of the interval from 1 to 1.1, is going to look at u of 1.1 minus u of 1, which is 1.21 minus 1, which is 0.21. Oh, so this little tiny interval over here in dx got doubled in size when I moved it over into the u variable. So I've changed the way that I'm cutting the interval up when I do this, right? When I slide from one way of looking at this to the next, I've actually scaled the way that I'm looking at the pieces of the interval. That's not linear. If you do the same exact thing, and you start moving the interval around, when dx looks at the interval from 2 to 2.1, it still spits out 0.1, because 2.1 minus 2 is 0.1. du eats the interval from 2 to 2.1 and spits out, okay, can I still square things? 2.1 squared minus 2 squared is 4.41 minus 4, which is 0.41. Oh, no. It changed the way, it's not stable. du ate this interval, which is the same length in dx. It's still a 0.1 wide interval, but now it's 4 times as large instead of twice as large. And if you continue this idea, if you measure the size of the interval from 3 to 3.1, the weight that that carries in u, du of, this is a total abusive notation, by the way, so 3.1 squared minus 3 squared, this turns out to be 0.61. So there's a stretching that's happening here. When we talk about distortion in these theorems, what we mean is, in dx, when we make our initial partition, all of the intervals are the same weight. They're all worth 0.1. It just cuts them up. But the change of variables that we've introduced is distorting the size of the interval based on where it is. And it's not hard to see that the particular way that it's distorting the intervals here is, well, it kind of looks like it's doubling you multiply the base thing by 2, but then there's also, you have to account for where the interval was. This is basically equal to twice 3 times the size of x. And this one was twice 2 times the size of x. Where the interval started dictated exactly what the distortion happened to be for that context. So when you write down du is equal to 2x dx, you are recording the distortion that the change of variables is introducing. This is telling you what does, when the u variable looks at one of the original intervals that you wrote down, these little dx's that you use to cut up your domain, 2x tells you what the distortion factor is according to that change of variables. And the point of that observation is, this is the derivative of the change of variables. So the derivative of the change of variables is dictating what the stretch factor is when you move things around. So there's more going on here than just a silly formula that you learn when you learn u substitution, where you just write, oh, well, whatever u is, you just immediately, without thinking about it, write down du is equal to 2x dx. You mean something geometric when you say that. So in your whole change of variables, if you think about the original integral that we wrote down, the integral from 1 to 4 of e to the x squared times 2x dx, what we're saying is not just that we're undoing the chain rule, but that if I weight the intervals correctly in the x variable, that I could recode this in the u variable because the partition is weighted the same way. Right? So these are identical to each other, not because of just u substitution as an algorithm, but because fundamentally we've changed two things. We changed the domain, and we changed the scaling of the part. We've introduced a function that keeps track of the scaling of the partition. So I changed the domain, but then I undid this stretch factor at the same time. So we have two questions to think about if we want to take what we're doing here and do it in two variables. The first question is, in fact, I'll move this over here so I'm not packing things in. So I have two things. If I want to do exactly the same game, but I want to do it in two variables. So I have a double integral over d of f of x and y dA. And in the polar coordinate thing that you've seen before, you write down one integral that looks like f of r dr d theta over a polar version of d. And then you can also write a double integral of f dx dy over a Cartesian version of d. The way that we got back and forth here was a change of variables in the same way that was a change of variables. Here the change of variables is t of r and theta is equal to r cosine theta, r sine theta. And what I want to do, I want to cook up a way where I can study this map according to the questions that introduces. The first is, I need to understand how a general map T changes the shape of the domain. So if I'm going to change variables, I have to keep track. In the same way here, I change this interval into that one. If I feed a change like this function a rectangle, it spits out a circle, or a chunk of a circle. I've changed the shape of the domain geometrically. And two, I need to study the distortion factor. How DAs change from this context to this one. I've changed the underlying structure of how I've cut up the set when I changed variables. So we're going to start with question 1, which is the subject of chapter 6.1. We're going to look at maps T that are change of variables and how they change the domains. And then in Sex 2, we'll talk about the distortion factor, which is called the Jacobian determinant, if you've seen that before. Okay? So in this context up here, when I write down r dr d theta is equal to dx dy, this guy right here is what I mean by the distortion factor. That's the thing that says rectangles on this side turn into rectangles on this side, but scaled by how far away they are from the origin. Yep.
This might be a bit of a silly question, but it seems like it should be the case that dr d theta is equal to dr theta. Is that a reasonable?
And dr, we'll come back to that.
Yeah. Okay.
Yeah, that there's a way that you can view that. Okay, so let's do a real basic example here. So we're going to start now with actual 6.1 content. Okay, so 6.1. So some notation here. We're going to let D star be a subset of R2. And generally, T is going to be a map from D star, which is our sort of initial domain, to a set D, which is our final domain. And we just demand that this is continuously differentiable. In practice, we'll be putting extra conditions on D star, but for now, it's just enough to consider these things as subsets. And so the notation that shows up frequently in this is D is equal to T of D star. So this is function notation for applying a function to a set. In words, you would say D is the image of D star under T. So let's, actually, we have an example right here. Let's write down an example of what one of these maps looks like. So if I wrote down, for example, we're going to consider the set D star to be equal to the rectangle 0 to 2 pi. Let's do 0 to 1 radius first. Cross with 0 to 2 pi. That's a rectangle. It's It's a rectangle in the r and theta variables. And I'm going to define a map T of r theta to be equal to r cosine theta, r sine theta. So that is our polar change of variables. X is equal to r cosine theta, y is equal to r sine theta. And the first sort of exercise you do when you're working with these functions is figure out what, hardly ever in that language, figure out what t of d star is. Right? What is the image of d star under the map T? And you probably already know this, but the way to visualize what we're doing here generally is that we want, we're starting with a rectangle over here, so between 0 and 1 in the r-axis, and between 0 and 2 pi in the theta axis. We've got this rectangle. That's our set d star. We're trying to figure out where that maps. When I apply the map T, where does it go? So there's a couple of different approaches you can take to do this. With nonlinear changes of variable like this, a lot of times what you're trying to do is figure out, okay, well, where, if I just like wrote lines through this set, where would they end up, right? So for example, if I wrote a line right here, so how about the line, I'm at angle 2 pi, and my radius goes from 0 to 1. So the blue line right there says the angle is fixed at 2 pi, and radius goes from 0 to 1. What ray does that look like over in this domain when I do that? So the blue line is supposed to be theta is constantly equal to 2 pi, r goes between 0 and 1. If you feed that into this transformation, what is it?
Straight line.
Straight line from where to where?
So radius from
0
0
to
to
1.
What if you cut through with a line right here at pi, say, and you let the radius, so now angle is constantly equal to pi, and the radius runs from 0 to 1. You go from here to here. And so as you cut through with these lines that characterize your rectangle, what you find is that you're going to get lines that look like this. But if I did it in the other direction, where is this? Notice these are all, this is actually already easy to see what's happening because these are all length 1, right? Where's this line? This line, the radius is constantly equal to 1, and the angle is going between 0 to 2 pi. That's pretty easy. Radius 1 and angle 0 to 2 pi, you're sweeping out the unit circle. If you picked a different line inside this set, this one, that's radius 1/2, but now the thetas are allowed to go from 0 to 2 pi. So you can see that the grid lines that we set up here in this picture correspond to the polar grid lines over there. So lines of like constant lines over here are pushed forward into these lines in this picture. Here's the issue with this particular map. What happens to all these points right here? Radius 0. I don't know if I call that a path, right? So notice that because radius is equal to 0, all map to the same point, right? So lots of points get mapped to that point. Every single point on this line gets sucked into a single point. So I don't know if you remember, but when we teach you this in calculus, we don't even allow this to be part of the points that are considered. We actually specify, Stewart is very careful to call that the pole and then exclude it from everything that he does. He's sneaky that way. And the reason is, this is not a transformation of coordinates that is 1 to 1. Every point over here that is not on this line has a unique point that it maps to. And every point over here maps back to a unique point in here, except for the origin, the origin in this picture. So something goes wrong there. So we'll talk about one-to-one in a second. Okay, another example of transformation that you've seen before, something like, let's look at the square from 0, 1 cross 0, 1, and we will set up the change of variables. T of x and y is equal to x plus y over 2, x minus y over 2. So there's a map. Eats things in R2 and spits things out in R2. And when we're visualizing these things, generally, and we're trying to change domain, oftentimes we do exactly the same thing I just did right there. I've got this square. I fortunately have lots of colors of chalk. So there's your square, 0, 1 cross 0, 1. And we look at the map T, and if we trace through what T does, if I'm trying to change my variables of integration, I need to know the effect that T has on the shape that we started with here. Now, if I know going in that linear maps take lines to lines, then I can sort of cheat my way into what the answer of this is. But I want to go through how you would do this if you didn't know that. So if I want to know the image of this, one way to do it would be to say, all right, I'm going to parameterize everything on that line segment. And it's going to have the form T0. Right? Y coordinates are constantly 0. T runs between 0 and 1. And if you do that, if you apply T to those points, T applied to anything of the form T0 looks like, okay, so x is equal to T. So you get what? T over 2, comma, T over 2. If you like, that's equal to T times the point 1/2, 1/2. Now the first point that we started with here was 0, 0. If you calculate this at 0, 0, you get, I think 0, 0 comes out, right? So there's T of 0, 0. T of 0, 0 is equal to 0, 0. Is it okay to observe that this is the vector form of a line? This is the vector 1/2, 1/2, and you're just scaling it by the vector t. So this is a line that you've built right here. What happens when you get t equals 1? So you're at 1/2, 1/2. So t of 1, 0 is equal to 1/2, 1/2. And the way that you got there was along this line pointing in the direction 1/2, 1/2. So the purple line is turned into this. You put in a line, you got out a line, you traverse the line, this is the segment that comes out. If you do the same thing here, so that got us from here to here. So the red point in this picture is this point. Where does 1, 1 go? So yeah, 1, 1 is 2 over 2, which is 1, 1 minus 1, which is 0. So you end up at 1, 0. That's a yellow line. I've got that right. Wait, is that true? Which line am I actually tracing here? This one. Sorry. This is not bad. That point and that point, the yellow and the red and the yellow dots connect like this. This is where you have to be careful. Which on my picture over there was the red line. We have one vertex left to go, which I will put in green, which is the point 0, 1. T of 0, 1 is what, 1/2 minus 1/2? 1/2 minus 1/2. And then you connect up your, have I mislabeled my sides again? Where's yellow? This is yellow. That's green. I believe I've got this correct. The origin touches 2 points. The yellow point is up here with a red. Yeah, okay, so I got that right. Now, a bigger question when you're calculating the images of these maps, and this is not always true, is how do I know where the inside went? Maps can flip the inside to the outside or the outside to the inside. You might suspect that this map is so easy that the inside of the square should probably stay the inside of the square. But if you weren't sure, how would you check?
I would demonstrate the inverse function.
No, I'd pick a test point. I'd pick, yeah, I mean, you can do that more generally, but like the Jordan curve theorem says that it's okay, that these will be like interior preserving. You just got to figure out where it went. Did it stay inside or did it go outside? So if I started with the point 1/2, 1/2, for example, and I calculated t of 1/2, 1/2, which is 1/2, comma 0. Oh, okay. So that point in the middle got mapped to the middle. Well, that's cool. It's a pretty nice map. Okay, so that means that because an interior point went to the interior, this is the whole picture. Now, I'm going to point something structural out here. This thing that we've written down is a really important class of maps called linear maps. There's an example of an important class of maps called linear maps where if I think about t of xy as being equal to 1/2 of x plus 1/2 of y, comma 1/2 of x minus 1/2 of y, I could have thought about this as a matrix multiplication. So this is an example of what's called a linear change of coordinates. So if t of x is equal to ax, t is called a linear change of coordinates. And linear change of coordinates are very easy to understand what they're doing for the following reasons. I don't know if this turns out to be a theorem. If you have a linear change of coordinates and the determinant of the matrix isn't 0, I'm going to write this down in a second, then lines map to lines and the vertices map to vertices. In particular, what that means is the theorem I'm going to write down, which is if you have a linear transformation or a linear map like this in terms of a matrix, and the matrix has non-zero determinant, parallelograms get mapped to parallelograms. I mean, if corners go to corners and lines go to lines, that's all that can happen. That's sort of the big theorem about these guys. So if, this is the way it's stated in the book, theorem, in fact, I'll put it exactly here. So the theorem says, if A is a 2x2 matrix, and you can imagine how this changes in more variables, the determinant of A is not equal to 0, and t of x is equal to ax. Then t transforms lines to line, transforms parallelograms into parallelograms. And vertices to vertices. Which means everything that we just did, we could have just kept track of by figuring out where the corners went. Furthermore, also, if t of some domain, if the transformation of some domain under a map like this has D, a parallelogram, so if the output was a parallelogram, then the input must have been. So essentially the theorem and its converse are both true. Of course, the reason that's true is because matrices have inverses when they have non-zero determinants. Okay, so the proof of this basically boils down to, if you guys took your 206 or 244, you probably learned the invertible matrix theorem with like Q parts of equivalent conditions having non-zero determinant. As soon as you say this, If you're trying to stay away from linear algebra, you would say that, but what you mean is the matrix is invertible, which means that the transformation is 1-to-1 and onto. Right? That you can go back and forth. It's an invertible operation. All right. So, in fact, this gives me a place where I can put a little bit of notation in here, or terminology. And I apologize. I know this is quite standard for those of you that are math majors, but there's people in here that aren't. So that condition basically boils down to, so if the determinant of A is not equal to 0, what you mean is that T is invertible. And ultimately what that means, what we care about, is that T is 1-to-1. And I'll talk about onto in a second. T is 1-to-1. So more generally, a map T from a domain D star onto a domain B is called 1-to-1 if every U and V in, sorry, I suddenly flipped up to like fancy language there, I apologize. But we'll just do it with a condition. If I know that T of X is equal to T of Y, implies X is equal to Y. So each input is assigned to a unique output is what 1-to-1 means, right? So we're taking this as a definition, this condition. But essentially what the condition says is if two outputs were the same, the inputs must also have been. So for example, this map that we wrote down where we have T of X and Y is equal to X over 2 plus Y over 2, X over 2 minus Y over 2, this is 1-to-1. I invite you to check that condition if you'd like to. But the map T of R theta is equal to R cosine theta, R sine theta is not 1-to-1 on this set that we had, 0 to 1 cross 0 to 2 pi. And secretly, the way that we fix it is we just don't let 0 be considered as a radius. Yep.
Could we also fix it with an inclusion and exclusion principle thing where we like then subtract off whatever area is getting counted twice?
Yeah,
and
the
cut it 0 in like everywhere.
No, so like normally the way that you do this, you might be able to do that, but normally the way you do it is you just delete spots in the domain. You basically only consider domains where the change of coordinates is 1-to-1. You just never allow this to come up. Okay, so when can you go backwards? When can you go backwards? So oftentimes we're interested in inverse problems. So what I mean by that is if I'm given a map T on some big set A, say, and T, yeah, so I'm given a map T and some set D. Remember, these are all in R2. Sometimes I want to find a set D star so that T of D star is equal to D. And essentially, the condition is going to be that I can do that as long as D is in the range of T. If my set D, so this happens, this is possible, if D is in the range of T. Right? I'm being vague about what the domain I'm considering here. I can find some domain of T on which D is in the range of the function. So we call that being onto. That is, I want to be able to find, so given a U and V in D, to find an X and a Y so that t of xy is equal to uv. That's the inverse problem here, right? I give you something in the range, I better be able to find something in the domain that it came from. That's literally the definition of a function being onto. So this comes up in practice, like in the vocabulary, which is why I'm doing it here. A function is sort of always onto its range, but so we say t is onto a set if for every, so easy to do that. Exactly the condition right here. For every u and v in the D, there is some x and y, so that t of x and y is equal to u and v, and some x, y in the domain of t. So that's onto. Okay. Now, of course, everything that we've written down so far, I mean, every linear transformation is going to satisfy both of these properties if the matrix is like non-degenerate. So, more interesting change of coordinates. That's going to be more. And so this, if we're doing this, we should probably do it in a case where the change of coordinates is more interesting, because otherwise you might think that the only change of coordinates that exist in the world that are ever used are the ones where you have a matrix transformation, which is linear, or you've got polar coordinates, and that's it. That's all that there is in the world. So let me give you a slightly more interesting set of coordinates here. So consider the following. Consider the map t of u and v is equal to u squared minus v squared 2uv. And let's, for the sake of argument, assume that u and v are both positive. I want to make sure that this is a one-to-one map. Let's let our set d star be equal to 0, 1 cross 0, 1. Let's actually see what happens to it. What does t do to that set? Draw t of d star. Okay. Yep.
I don't believe this is one-to-one.
Oh, it is as long as we stay in one quadrant. I'll draw it. It's not, it is on the range. So let me just draw it and then we can argue about the conditions here. So we're going to start by doing the same thing I did before. I'm going to draw myself up a little square here because I'm a caveman. I've got nothing else to do. So there is this side. And here is this side. Here is this side. And here is this side. And let's actually see exactly what the hell this thing does to the set we're looking at here. So I start in u and v on the red side right here. And on that red side, I think it's the case that every point on here has the form u comma 0. Okay, so what does t do to u comma 0? T of u0 is equal to u squared 0. U runs between 0 and 1. U squared runs between 0 and 1. So the red side gets left alone. Oh, this is going to be a really easy map. Maybe it's secretly just the identity. How about the green side? Everything on the green side, which has the form 1 comma v, let's actually do the other side first, the yellow side. So maybe this will be more enlightening here. So if we do the same thing to the yellow side, where we have points of the form 0v, and you evaluate t on that line, so t of 0v is equal to minus v squared, comma 0. And v runs from 0 to 1, which means now we're running from the origin out to the point minus 1, 0. Okay, something weird happened there. So I've already basically taken my square and I've just unfolded it. So you should already not think there's nothing linear about what I just did right there, right? If I took a straight, angled lines and I've pulled it apart into something where I've rotated into one line, notice this doesn't even preserve vertices. The origin is now in the middle of an edge. This line, all the points on this line have the form 1v. Let's go look at that. Okay, so t of 1v is equal to 1 minus v squared comma 2v. So what I'm going to do is I'm going to work with the parameterized formula here. This says that x of x is equal to 1 minus v squared, and y is equal to 2v, which means y over 2 is equal to v. And if I took this and plugged it back over here to get a relation between x and y, I'm going to get x is equal to 1 minus 1/4 of y squared. So eliminating the parameter here says that the image of the green line is a parabola. The parabola has vertex 1, 0, I think. And it opens to the left. And when x is equal to 0, y is equal to 2. Of course, the part of it we're considering is just this part right here, from this point to that one. So this is a part of the parabola. X is equal to 1 minus 1/4 of y squared. And the purple side, which looks like u comma 1, if I play the same game, t of u1 is equal to u squared minus 1 comma 2u. If you do the same elimination of parameters here by writing x is equal to u squared minus 1 and y is equal to 2u, you'll end up with x is equal to 1/4 of y squared minus 1, which is a parabola that opens this way. And then I ask you to trust me that the interior of this region gets mapped to the interior. You can check that by verifying on a single point. And so this is about as nonlinear as a transformation comes, right? I mean, we've completely destroyed any sense of lines here. We've taken the corner of a corner and turned it into a not a corner. And more generally, if you think about the grid lines that we've introduced here, so if you step back and say, okay, well, that sets up a change of this domain into this domain, more generally, what does the coordinate system look like under this transformation? So there's a coordinate system on the first quadrant here that gets pulled into a coordinate system on the upper half plane on this side. So you can imagine that if you made a larger square around this thing, I don't have more colors of chalk, so orange in here. So if you did something like this and had a line out here, well, the vertical line that goes through that point is going to get pulled into a parabola that opens like that. And then you might wonder, well, what happens to horizontal lines? Well, they get pulled in the same way. This horizontal line up here gets pulled. Actually, what I wanted to track what happens to this set right here. So where does that square go, right? This square has a green edge, an orange edge, a purple edge, and I guess if we extended this line, it would continue to have a pink edge. So you should be able to see that what's happening here is this is actually setting up a coordinate system where these are supposed to be the same size. I apologize about that. That this square ends up mapped into this bit right here. In fact, I think maybe it's the whole thing. No, that's right. And you can check because you're saying pink side is pink side, green side is green side, orange side is orange side, and I guess, oh, I missed this part. The purple line comes through, which dictates the last side here. So not this. The edges stayed the edges. So if you want to think about tiling this with little squares, over here, you've tiled this space with chunks that sit between parabolas. So this change of variables is used all the time in weird applications because for some reason physicists and engineers like to study functions that have u squared minus v squared and 2uv in it. So this kind of, oftentimes in practice what you'll have is you'll have a function set up on a domain like this and it sucks, and so the way that you pull it back into a square is you undo that transformation to get back to the rectangular grid. if the domain is hard, you can exchange the difficulty of the function for ease of the domain by coming backwards to the sets that these things came from originally. Okay, now, any guesses about what the distortion factor should be here? Because, I mean, this introduces some little distortion factor. If I put a little tiny square right here, so just a little itty-bitty square at this corner right here, that little itty-bitty square is going to get turned into a little itty-bitty chunk of the curve, the set between two parabolas, right? So that square is definitely being, I think I've got the right spot, yeah. So that little square is no longer, I mean, it is a square before you did the transformation, but like there's a distortion factor that happened, right? That little dA under this map has turned into something that's not a square anymore.
2u minus 2v, and then also like in the other direction, 2v plus 2v.
Yeah, so here's a preview of what we're going to do. I can describe the change that's happened here in terms of the derivatives of the transformation in the same way that we went from du to dx by taking u as a function and then du was equal to the derivative times dx. The distortion of this little bit into this shape is going to be calculated, at least in part, by a matrix where I take the derivatives of each variable. So those are the changes of the first function, and the changes of the second function. Oh, is it literally the same? No, okay. 2v, 2u. So we've studied this already. This is a Jacobian matrix. It's the matrix of first derivatives, but now it's the matrix of first derivatives of this map. And it's going to turn out to be the case that if I want to know at a particular point in space how much this little bit changes in area relative to this, I just take the determinant of this. So the determinant of this is going to turn out to be the thing that dictates the distortion of that little bit to that little bit. So of course, that's the end of the class today, so I'll have to leave you on tenterhooks until next week when I'll do this. This is actually the content of what's called the change of variables theorem, and that's 6.2. All right, have fun drawing maps. I think 6.1 has some amusing exercises. I encourage you to use visualizers to do this. You don't have to do it by hand if you don't want.
See you later.
Yo.